Let me wait for say 2-3 more minutes. If your friend, unfortunate that I couldn't take your previous classes because of some health issues I had. Now I hope we'll be able to overcome the lag whatever we had previously. I hope that I'm quite audible.
Yes, sir.
Yes.
Thank you. So I think the illumination engineering portion of this utilization subject is a 50% of the entire curriculum. It's very unfortunate again that we couldn't perform few laboratories in your third year, but generally we used to do every year. So some basic understanding can get developed from there also, because this illumination engineering as a subject is itself a very much application oriented. So that's why whatever we are going to discuss today and the coming day, I hope that we will meet in person in a physical mode, in a normal conventional classroom teaching, because this kind of PowerPoint based teaching is difficult with this subject. We need more and more chalk and talk methods. Let us start about the topic. So illumination engineering as a whole. So what actually we have in our curriculum. In today's class, definitely we'll be talking a lot about the technical background, but mostly we'll be focusing about the curriculum, what we have within this topic, the illumination engineering as a whole. So actually the entire topic so far, whatever we have, that I have divided in a different modules. Let me tell you very frankly, few of the questions will come to in your mind, because this is a topic which you are getting acquainted for the first time in your curriculum. You will be getting some kind of terminologies, apparently sound similar, but not that. We need to identify, visualize, and connect them, and how that is related with our engineering topic, that is also required. Because today, one of the significant global research starts with illumination engineering. So if you can contact your seniors who are doing their say masters and PhD in different institutes throughout the globe, you'll be able to know that the illumination engineering is the one of the very booming area where lots of research are there. Why? What is illumination engineering? Today we are going to search for that answer, that how can we define illumination engineering as a subject, and then why we call it engineering. So those portions will be discussed today. So that's why the module is defined in such a way you will be able to get the different components individually, just like light source. Fundamentally, once we are talking about the illumination engineering, the module 1 mostly will talk about the classical approach. What is classical approach? The classical approach, say for an example, what do you mean by the term illumination engineering? Apparently, it will mean that it's to put some light somewhere to require to justify your all the needs, the visual needs. So that is the fundamental idea what we always think about lighting. That means we will put the light somewhere and we should ensure that better visibility should be achieved. But illumination engineering is not that. There are several areas, several components which are very much allied, but we'll say that illumination engineering is not only to put light somewhere to have a better visibility. It is definitely a very important aspect, but at the same time, we need to ensure your performance. Performance doesn't mean you need more and more light. Just a simple thing. So that's how my module 1 on illumination engineering and module 2 on illumination engineering will differ. Once the course, say 13 years back, once I have started teaching this, taking these classes on illumination, on that time, whatever outlook I had, and today it has completely changed. So that's why, sorry, today I need to identify the illumination engineering 2. That module will talk about some paradigm shift in this field. So paradigm shift, I think you all know, that's basically nothing but to have a very positive mood for some betterment. So here the betterments are very much inherited. How? Just a simple thing. Illumination engineering module 1, the physics of light, the different radiation law, that we all definitely will talk. But before that, again and again, I want to talk about the module 2, which is very new, which will make you much more confident to think about the classical approach. So what it actually talks about? It talks about the human-centric approach. Say, if you're, let's think about your cases, that if you have a post-lunch classes, after 2 p.m., whatever classes you have, mostly you are trying to make yourself very much concentrated about the topic. Maybe the topic is very interesting, but it doesn't mean that always you will be able to connect exactly the way you are thinking of. You may feel a little bit sleepy. So that means you might be thinking that this is a natural process, but how to get rid of this? Is it to say something? The very silly but very simple example I want to share with all of you, that sometimes somebody is, maybe I am taking your class. So the utilization and elimination classes, possibly you have managed your previous year's textbooks and notes. Very first day I am telling you, unfortunately I can provide you some notes. I will be providing some textbook. There are several textbooks, and neither of them are from Indian author. So I have all those books. I will never ask you to buy any books, but once it will be possible, you come to me and make a photocopy of that portion. So you need not to make that photocopy of all the books. At least 10 to 12 number of books we have to consult this portion, and all are definitely written by the foreign authors. So that's why we can use this like that. So that's the practice we will be going to follow. So don't ask me for any notes. Unfortunately, I can do. I am a very lazy person, and finally, I have been managed myself to prepare this PowerPoint presentation that I will share with you. And for the rest of the materials, whatever study materials definitely you will need, I will be sharing the books with you. So I'll ask somebody from your end to come, whoever will be possible, come to my room in the department. So I'll be sharing the book. Make a photocopy of that and make a share and circulate among your friends. So now come back to our actual discussion. So maybe I'm taking the utilization classes. So what happened, every post-lunch classes I have, 2 p.m., after 2 p.m. or 2:30, whatever classes I have, you are feeling sleepy. This is quite natural because we are feeling sleepy because of some other part. So we can't ignore the activity of the human brain. So that is a very, very important area of research throughout the globe. You know that the cognitive science has become so many important aspects, and lots of research are going in this field because to know how your brain behaves. So now that's why I am writing so many things in your boards, and you all are making your eyes mostly widely open because you know that I am your teacher. We will be definitely meeting many more times. So that's why you are getting forced to make your eyes widely open. But what happened? You are not getting it. Maybe I'm drawing something on the board or writing something, some calculation, some kind of derivation. I'm doing that, but it doesn't mean you all are accepting in the same way. Why? Because on this condition, your brain is getting regulated. Your human performance is getting regulated by the two hormones. One is, the melatonin we call, and another we call cortisol. So basically the balance between that two hormones will trigger your performance. So if you have a rush of melatonin, you will feel sleepy. And that is quite natural. So that means after 2 p.m. or 2:30 p.m., whatever classes you are attending, if you have a rush of melatonin in a natural way, what we call human circadian system, sleep and wake cycle. So that's why you are feeling sleepy, because that is quite natural. Now, if we are being able to trigger a rush of cortisol instead of melatonin, then we will feel activated. So that's how your brain performance will enhance. How that can be done? The easiest way, after writing, suddenly I have turned towards all of you and say that now, students, what I am going to talk about, this will be your coming semester topic, the most important topic, and the question will come from this portion. If I say that, immediately your alertness will increase. What is that? To me, this is nothing but a visual stimulus. You might be thinking that, sir, why in introduction class of illumination engineering you are talking about this? I am trying to relate that. Basically, what actually we are doing, I am using a auditory stimulus. This will be your semester question. That is an auditory stimulus. So your brain, a very complex parameter, a very complex, structure. I am talking about a very small structure portion of the brain, what is called suprachiasmatic nucleus, abbreviated like SCN. If you Google, you will be able to get the detail. Later on, we will be referring few times about this term. Don't be scared that I am not talking about the brain anatomy, but we need to refer sometimes about those. The suprachiasmatic nucleus part of the brain, who is responsible to control the two hormones, your activity hormones, the melatonin and the cortisol. Now, what happened? That's the auditory stimulus. Once I had said, to the auditory path, there is a connection to the human brain. There is a connection to the suprachiasmatic nucleus. And once it will reach, immediately that will trigger to your brain and SCN, that means the suprachiasmatic nucleus part of the brain, will control the secretion of the two hormones, and the cortisol will increase. Melatonin will get suppressed. So that's why you will feel activated. So far, whatever I have given in that example, I have never talked about anything related to the lights. So what else we can do? The else is that instead of saying that this will be your semester question, instead of saying that auditory stimulus, if I change the light of your, that maybe the intensity of the light, maybe the color of your light, if we do that, so that may lead to a change of hormone. That means the cortisol can be made more aggravated. So more and more the rush of cortisol will definitely suppress the melatonin and you will feel active. To refer that, it's a very interesting experiment, because today it's an introductory class. We will be talking more. During 1990s, during that topic, if you have any difficulties at any part of my lecture, just feel free to contact. Okay, feel free to tell me. Don't feel shy. You interrupt me and can share. Some portions where I will precisely say that don't interrupt, let me finish. That I will tell you separately, but otherwise feel free to interrupt at any part of my lecture if you have any doubts, relevant doubts. So, okay. So that another interesting thing. This is a in illumination field research. Whatever we had, we will be referring.
Sir, we cannot see the slides, sir.
Oh, the slides I am not showing because right now there is nothing in the slides, so that's why I am not showing the slides. I am just saying the slide portion will come in the next portion, so that's why I am not sharing the slides right now. I hope that you can see these introductory slides.
Yes, sir. You can see this illumination engineering.
That's the only. But the component, whatever I am talking about, those slides are not there right now. That is, as a whole, I want to explain. Then we will come back to our slide exactly and what actually we are talking about. So, as I was saying you that human performance, the illumination engineering research was under a big, very significant paradigm shift occurred during the year of 1990s. What is that? The very well-known scientists from Serbia, Zokic and Kostic, they are the very renowned scientists, mainly the Technical University of Serbia. Kostic was the head of the Department of Electrical Department. So they were doing that research where they were planning to identify the effect of spectrum of light on human performance. You know, I think many of you have noticed that once you are traveling to the road, sometimes we have yellow light. Previously, during the old days, during my childhood, I have seen yellow light, or that was the only option. Now you have seen most of the roads are getting converted with white lights. Now they are getting converted with LEDs. So that means there is a change of spectrum of light.
Previously, was on that.
Yeah. Yellow light, now it is becoming white light. So definitely the question may come that what is the reason behind the white light? Let me tell you very frankly, in our Indian context, there is no such reason. People hardly bother about, especially in our corporation, hardly bother about that why they will shift to white. But there are the basis, technical basis. So Caustic and Zocchi, they were doing that experiment. Their intention was to know about the performance of human being under white spectrum or yellow spectrum or different shades of white spectrum. So how that changes, they were about to identify. So they did lots of experiment, and definitely the outcome was not that effective. So they were searching from some real experiment. During that, Peter Zokic's friend, one of friend, at a call center in Serbia. So what he said that one day that my call center is not working properly because I am in a huge loss, because most of the time I've seen my employees are sleeping during nights. So that's why my business is under huge loss. So I'm planning to shut down my business. So Zokic said that, can you spare your setup for 3 months to us? He said, why not? I have invested a lot, but now I am losing. So definitely I don't have any more interest to continue, but so many years I have already invested. So that's how I can spare for 3 or 6 more months. So what Zokic and Caustic they did, they took that. They have only changed the lighting pattern of that and asked their friend that you allow your office to run its normal schedule. After 3 months, there was a remarkable change. It was identified that the employees who were about to sleep during nights, actually, once they came to the office in the midnight, they were about to sleep, they were not being able to feel sleepy. They are not being able to sleep, and they were complaining that we can't sleep. There is some change introduced in our workspace which are not at all allowing us to sleep because we are not feeling sleepy. So in a midnight, if you are not feeling sleepy and if you don't have enough thing to gossip about, so what else you will do? You will start doing your work, and definitely the work performance has improved. So then Caustic and Zokic said, "That's very good. Can you spare the same setup for 6 more months?" So the friend said, okay, you take it and continue the experiment. And after 1 year, they published that paper that if you have the bluish content white light in a night time for the indoor work, the performance is getting enhanced very much. You will not feel sleepy. And at the same time, they said at each different spectrum, how human sleep and wake cycle, that is what we call human circadian system, that is getting affected. That can be modulated. So the outcome of that research, the story, whatever I've shared with you, that was revolutionary because that is a very clear understanding that your human brain is very much contributing, very much reacting towards the different spectrum of light. But after that, it's very unfortunate because this kind of experiment, human related experiment, should have ethics clearances. So as they did it, absolutely hiding the actual truth to the individual, so that as a result, what happened, the experiment, after successful experiment, they both of them were got convicted because that you are doing experiment with the human subject without their consent. It's not right, because after that, many of the subjects, many of the employees, they have suffered from the issues like metabolic disorder, basically because the sleep and wake cycle was interrupted. So that is an example which very clearly says that the light can contribute to your performance. It is not only required to see something. So with the investigation, what came after their result, whatever was coming with this call center work, so the experimentation was started to see what actually we have in our human eye. The fundamental anatomy of the human eye, say, I think all of you know, there are the two type of receptors we have, rods and cones. We know the dark adapted one and the color or pigmented one. There is a rods and cones. We will be talking about them and their performance in the coming days. But the only interesting thing is that rods and cones, whatever we have, at the same time, we have another very third graded photocell present in our human eye. Why I am using the term called third graded? Third graded term is used to indicate something which is not that quality-wise not that accurate. So once we are talking about first graded, just think about your rods and cones. They are responsible to capture the image. Say all of your eyes are, eyes are widely open towards your maybe your mobile phone or maybe your computer screen. So you are capturing some image. So that means your rods and cones are responsible to capture the image. But the third cell, whatever I was referring, that is a third graded cell. It is not responsible to capture the image. It is placed in your retina, but the function of this cell is just to sense whether some amount of light at all present or not. You know, the photo cells, we'll be talking about the photo cells, the sensors part in our this subject. Once we will be talking in the coming days, the different sensors and the lighting control system. There we will see that there are different type of photoelectric sensors we use while we are developing a lighting control system. It starts with the very classical LDR, light dependent resistor. That may be photodiode, that may be phototransistor, that may be photomultiplier tube, that may be CMOS, that may be charge coupled device, and that may be with any extent. Your LDR, which is a very cheapest solution, what is happening with the LDR? So the resistance will vary with the light. And at dark condition, your resistance will be much higher. So if you have a light, the resistance will reduce. So that means you can have a curve. But that LDR is not capable to capture an image. To capture an image, you need a very high accurate cells like charge coupled devices or CMOS. What actually we have with the all digital and different type of SLR cameras. So that means it is very clear the third graded cells are there in the cell, in our retinal cell. So they are situated just to capture or sense whether the light is there or not, but this is not at all capable to capture the image. This kind of pigmented cells are called IPRGC. Just I am opening a Word document to write you down. Just IPRGC, intrinsically photoreceptive ganglion cell. So this is what we call IPRGC. I'll be sending that later on. IPRGC, intrinsically photoreceptive ganglion cells. What is IPRGC? What is the role of the IPRGC? The IPRGC is nothing but a source, better to say a receptor, which will be situated at the retina to sense whether the light is there or not. What is the spectrum of the light? What is the amount of light? Based upon that, it will send a command to a part of your brain. Already I have mentioned that is suprachiasmatic nucleus part of the brain. And that's how there is also an alternative channel. Initially, I was talking about the auditory channel. Now I'm talking about there is an alternative channel through human eye, through the intrinsically photoreceptive ganglion cell towards your suprachiasmatic nucleus part of the brain. Just see, this SCN is not at all related with your visual performance or your visual activity. There is another different part of the brain, which we call visual cortex. SCN is not as part of the visual cortex. SCN is responsible for your entire central functionality. It is also responsible for your motor. That is after that, the nearby portion is our motor cortex. So the motor activities will be regulated by that. So that's why what I want to tell you is basically through the same path, the auditory path as I was talking about, there is another route, another channel through the human eye to the brain, which is not directly related with the visual part. That is related with the only non-visual effect of light. So that will regulate your performance based upon the non-visual effect. So that is what actually we are always thinking of, the non-visual effect of light. So that is why let us come back to our this topic. The illumination engineering 1 will be mostly talking about the classical approach, and the classical approach, the mathematical portion, the formula, the equations, whatever we are going to talk about, that's mostly talking about the visual. So that will not talk about your this intrinsically photorealistic cell or your
Sir, your voice is breaking.
Sir, you are not audible.
Sir,
Yes,
you are
sir.
glitching your voice. The network is probably unstable.
Still the same.
Yeah. Can you is it audible now?
No, sir, it's still not properly audible.
It's showing that your network connection is lost. Just wait. ক্লাস নিয়ে আসছে একদম হ্যাঁ থার্ড ইয়ারের ক্লাস নিচ্ছি নেট চলে গেল
Now, sir, it's okay.
but in my case it is still showing you lost your network connection trying to
ওটা
reconnect.
রিফ্রেশ করলে ঠিক হয়ে যাবে
Okay, thank you. So finally sir replace হলো
হ্যাঁ স্যার এখন ঠিক আছে
okay thank you হ্যাঁ স্যার বসুন না আমি থার্ড ইয়ারের ক্লাস নিচ্ছি আপনি বসুন চা খাবেন দাঁড়ান আমি একটু just 1 minute break. Okay.
Okay, sir.
Okay. Just stay there, stay online, don't leave. I'm coming.
Okay.
Is it now okay?
Yes, sir.
Sorry for the interruption because we had some issue with the internet. I don't know. That is third time the internet got lost and I got disconnected. Anyway, now is it audible?
Yes, sir.
Yes, sir.
Okay. So what actually? Let me continue whatever actually I was talking about.
Yeah,
Here,
are you in college?
huh?
Are you in the department?
Yeah, I'm in department now. I'm in department now. Hello.
Yes, sir.
So that is why I was planning to use department's internet, and that's the problem. So basically, let us come back to our discussion. That is, in this case, the non-visual component, whatever I was talking about, now that is converted to our visual. So that means the non-visual portion is definitely the most important area today, because here your entire performance will be regulated by the light. So as an example, 3 minutes back I was telling, this portion we will be mostly dealing with the quantity of the light and quality of the light, but we will be not going to talk about the human-centric approach as a whole. So that means all the lighting design and their system will be aiming about to ensure your better visual performance with a less use of energy. So that is also very important, the energy calculation, and to develop an automatic control system which will sense the light and accordingly control the entire. So this under this module in the classical approach, the first part is the physics of light. So this portion I should not spend too much of time, because I think many of you are quite well aware of that. Since our +2 level physics, we already have gone through many times the physics of the light. This is the only for connectivity of our previous knowledge. I have mentioned that. That is, we know that light as a wave, light as particle. So the corpuscular theories are there, the quantum theory in 1905 and 1925, the de Broglie developed the hypothesis which the combined the wavelength and corpuscular theory was explained, well explained. So that's why we can say it's an electromagnetic wave, but at the same time, it can be defined like the photon. That means a bunch of energy. So that's why particle with a bunch of energy. So that's why this is the classical approach which how we can define light, and definitely the different phenomena. If we can talk about, I hope you all can recapitulate that while we are talking about the particle theory, some of the phenomena cannot be explained. Once we are talking about the wave theory, some of the phenomena cannot be explained. So that's why there will be a combination. Sometimes we can treat it like a particle, but undoubtedly it's an electromagnetic wave. And so far human eye is concerned, if I ask you to find out the wavelength, so you can, I hope you will be able to find out that what is the wavelength. But human eye, from the visible point of view, once I was talking about, there is a range which the rods and cones can accept or can sense. So what is the range? The range is 380 nanometer to 780 nanometer. That is what we call visible band. So energy within that 380 to 780 nanometer can be only perceptualized by human eye. So that's why this 380 to 780 nanometer, this region, this portion we call the visible band. Now, your light source, you really don't know how much energy is there. So this is another very important point while we are talking about the visual part. That means light source radiates most of the energy. Out of that, how much energy is getting converted as light, that is very important to know. You might be thinking that why I am talking about that. Any idea while we are talking about the different light sources with the different big family of the light source, which starts with the very fundamental Edison bulb. Now today we have the LED. I'm not talking about the very precise non-specific sources like plasma lamp or something. But if we see the journey at a glance, so the one of the parameters which actually governed to develop a light source was also the efficiency of the source itself, because it consumes an electrical energy. Do you have any idea what is the efficiency of an incandescent bulb? What generally we do use? The forefather was definitely, started with Edison's concept, then the Coolidge, and after that today's bulb we have. So Any idea what is the range of efficiency for incandescent bulb? Anyone? Am I connected?
Yes, sir, you are connected, sir.
Okay. So anyone?
So very low, 5-10% maximum.
Very low, 5 to 10%, right? Anyone else? You are right, Shreya, but the only thing is that while you are talking about efficiency, I can share an interesting story with you. A long back, once I used to work 16 years back in a power station. After joining in a power station from here, suddenly I have seen it was there was a motor bay. You know, big HT motors were placed for weekly overload. So I have seen the stator windings are placed and the rotor windings were taken out of that, the HT induction motors. Now, within the stator windings, there are some incandescent bulbs placed for a long period of time. This was mostly during the rainy days. So I got absolutely surprised. So I asked the in charge, I was just a graduate engineer. I asked the engineer, my senior, that what happened? Why you are putting incandescent bulbs there within stator winding? So he said, this is a very good way because mostly during these phases, rainy days, there will be a chances of contamination of moisture within the windings and also to the insulation. So that's why we all know the insulation resistance values are becoming very poor. So for that, we need a continuous heating. So I have seen in a HT motor, big HT motor stator winding, 200 watt lamp was placed at least for 24 days up to 7 days a week, complete week. So why I am giving that example is just to tell you that here my incandescent bulb is used like a heater. It's a good source of heat. Okay, so far efficiency is concerned, if we can think that is an input-output ratio, you all know for the generator, for the transformers we have calculated. But here this input-output ratios are different. So that's why if we do calculate every time the value will be something. For incandescent lamp, this value is coming something like 70 to 80%. You might be thinking that after a source having 70 to 80% of that, I am saying this is a poor. No, Shreya was right. The 5 to 8, once we are talking about the source used as a light. So my input energy is electrical energy. So it's 100% input. Out of that, there will be some non-radiative losses of 20%. So if you remove that, the remaining 80% is converted as output, and out of the 80%, a very small fraction is getting converted as light, and most of the energy, is getting converted as heat. So that is a problem with the incandescent bulb. So it can be used like a very good heater, but it as a light source, once we are using the same, the amount of energy which is converted is a very small fraction. So that's why there was a necessity to introduce a new efficiency term for a light source. So that's why the efficiency of an incandescent lamp, if somebody asks you, is not that poor. It's almost 80%. But the light, as a light, its efficiency is poor. That's why a new term is evolved that is called efficacy. EFFICACY. The efficacy is, the unit is lumen per watt. What is lumen? In coming days, we'll be talking. The terminology is more precisely, but this is nothing but the unit of light flux. For today, we can loosely take this is the amount of light divided by the electrical input watt. So this term will only indicate, this efficacy term will only indicate the fraction which is getting converted as light. So that's why incandescent lamp, the efficiency is very, very poor as a light source. It's only 5 to 8%, as you said rightly, if we use it like a source. So the efficacy is poor, but the efficiency is not that poor. Clear? So that is why here, why I have given this example, just to tell you that the total energy coming out from a source, it will encapsulate different range of wavelengths. But out of that, what is the light? To know about that, I need a filter. And what is the filter? That is the 380 to 780 nanometer, the visible band. So energy which is coming between 380 to 780 nanometer region, we can call it light. But before 380, we all know that is an ultraviolet region we have. Just after 780, we have infrared region, and that's how we can have alpha, beta, gamma. Even the 50 hertz sinusoid, B equal to n lambda, you can find out the equivalent wavelength, and unfortunately, it will never come within 380 to 780 nanometer. So that's why you will not be able to see that properly. So that is the most important criteria once we are talking about that case. So here, why I am telling you, because our next topic will be relating lumen to watt. Here we will see the total energy coming out from a source that will be given an input, and out of that there will be a small fraction taken. That small fraction is basically the human eye curve that will be used to identify how much quantity of input energy is converted as light. Okay, so that is what actually you're talking about. Now the generation in this, let us come back to our slide. So in this slide, we are talking about how the light source generation can be divided. There are different methods by which light can be generated. Fundamentally, already I have given you an example, incandescence, and rest of the family is called luminescence. Sorry. So the incandescence means once the current is passing through a conductor, it will get heated up. So that's why some amount of energy will be converted as light and most energy will be converted as heat. So that is what we call incandescence phenomena. And luminescence, the rest of the procedure by which light will be generated will fall under luminescence. So luminescence is a big family. Just an example I can tell you for fluorescent lamp, which is nothing but discharge lamp. What we have, there is a tube, both sides we have two electrodes, and it's filled with the gases. Maybe the low pressure mercury vapor. Our fluorescent lamp is low pressure mercury vapor. I think you all know. So here with a very low pressure, we have mercury vapor gases placed within that. So in this way, you can have high pressure mercury vapor. You may have sodium vapor. So different type of gases are there for entire discharge family. The idea is that we are applying a voltage across the electrode to ionize the gas. So we are allowing the discharge phenomena within the electrodes. And that's how there will be some acceleration which will occur because of the discharge, and that will indirectly be a source of light. This is what we have, the discharge lamp family. Today we are talking about LED. What is that? Light emitting diodes. What are there? It's nothing but a PN junction. The way we know for a traditional any diodes, it may be Zener diode as also in our this PN junction, in the junction region, electron and hole will recombine, and as a whole some energy will come out. We know the result will be some energy will liberate. So once the energy will come out of that process of recombinations of electron and holes, that energy, wavelength of that energy will decide whether it will be light, whether it will be heat. Interestingly, if the energy, whatever is coming out of the recombinations, if the wavelength of the energy is falling between 380 to 780 nanometer, we can call it light. And if this is more than 780 nanometer, that is a very common diodes. If we are talking about the power diodes also, this is the most challenged part because the energy coming out of the recombinations are mostly in the IR region. So that's why my junction of the diodes are getting heated up. So that's why you need to design a proper heat dissipator such a way you can dissipate that energy from the junction. But for LED, because of the very specific doping material we have, it may be just gallium arsenide phosphide, a single example. There are several types of doping material. Instead of gallium or instead of germanium or silicon, if we use that type of doping materials, then the energy, whatever will come out, it will have some amount which will fall under 380, 780 nanometer, and rest of the amount will go as IR. So that is also a challenge for LED. So your light will come out, at the same time the junction will also get heated up. So that will come under luminescence. So why I have given two examples, we definitely will try to talk about those different light sources and their operation later on. But here my intention is to tell you that the luminescence, the discharge lamp, the LED, all will come under luminescence. Now this black body radiation, in coming few days we will be
Sir,
spending.
screen is not visible to us.
Oh, so far it's not. Oh, possibly.
Oh.
Sorry, because of the disconnection, the screen has screen
Yes, sir.
Now I hope it's ইউনিভার্সিটির ইন্টারনেটটাতে না সত্যি কাজ করা খুব মুশকিল। Now is it visible?
Yes, sir.
Sorry for this interruptions. So incandescence and luminescence. So that the slide actually what I was talking about. Now the black body radiation we need to refer. I'll be spending lots of classes on the black body radiation in the coming days, where the two types we will be talking about. Okay, very clearly, because in your class 2 level physics you also have gone through the black body and their properties. But here two type of things we'll be separately discussing. One is the property of the black body. There are the different properties rather of the black body. And another set will talk about the radiation law. So don't get confused that both are same. So we will be definitely talking about the properties and this radiation law separately. We will be trying to talk about those individually, how the properties are different with respect to the radiation law. But in this black body radiation law, why the black body is required, I'm right now today not talking about this. As a whole we are going to talk. So black body radiation, as all of we know, once we are talking about the, just again a little recapitulation of maybe in your class 8 textbook of physical science. On that time there was no demarcation like physics and chemistry. So if you can recall, there was a chapter called units and standards. And the last units, whatever actually standardized, was candela. So on that candela definition, it was used a platinum black body operated at its solidification temperature of 2042 Kelvin. 2042 Kelvin is the solidification temperature of the platinum black body. So that is so far the practically realizable black body exists. Now that is actually situated at our National Institute of Standards and Technology, that is situated at United States, so NIST. So they are offering that particular platinum black body, which was used to define the candela, the last definition of this. So in our case, definitely we will be referring this platinum, the only practically realizable black body. That's many times. But we will not be able to use the other black body card, because mostly once we are talks about the different black body models, those will be talking about the theoretical model, which was started a long back with the Rayleigh-Jeans model, then Planck's model, then Wien's model, then Kirchhoff's model, the different model of the black body. We will be talking about those in nutshell, but mostly what actually we have in black body model. What do you mean by black body models? The model means in my x-axis the wavelength will be represented, in y-axis the energy coming out, the intensity of the energy or power density per unit area of the source. So that can be represented, but another input is also there, another variable is also there. That variable is operating temperature. So this is all we know. The Wien's displacement law, you know, that is what it says that for a black body, I'll ask you to recapitulate that. Black body radiation law says that if you are increasing the operating temperature of the black body, the spectral power distribution of the black body will shift towards the shorter wavelength. That is what we know.
Yes, sir.
I think you all can recall that mathematically lambda max into t equal to constant we have mentioned many times. So more and more t, so the lambda max will be shifting towards the shorter wavelength. But the value of peak value, the value of the maximum intensity, that will vary accordingly. So that is not shifting, but the wavelength at which the peak will achieve, so this will be shifting towards the shorter wavelength. So that is a very, yeah.
So what's the input of the energy? I mean, how for energy conservation law?
Yeah.
If
So
there is any input.
No, actually input is here you are increasing the temperature. Here your temperature can be defined like a stimulus. So once you are adding some stimulus, so the entire area under this curve will indicate the because of stimulus how much energy is converted. So if you can see to this curve, so in my y-axis it is nothing but watt per centimeter square or millimeter square, forget about. So this is the power density, and x-axis there will be wavelength. So definitely it will be shifting towards shorter wavelength, means the peak will be reaching towards short. But as a whole, the area under the curve, if we can consider, that will not change. Are you getting my point? So the idea is that, rightly you said that energy conservation, it's not violated, because once we are talking about the energy conservation, here we are basically concerned about the total energy, not how much is light, how much is say ultraviolet, how much is heat. Are you getting my point? So once we are talking about the source, again and again I am telling you, this curve is called spectral power distribution. That is an input to of source. So more and more temperature, that value will definitely change, but the peak will be shifting towards shorter wavelength. So that is a property, but this property mathematically established, but this property has a physical significance too. The physical significance is that the area under the curve definitely will vary, but maybe whatever black body property I had before, say 2000 K, if I operate that, it will be shifting towards the light. Let me make it more simple for you. So can you see the curve in front of your screen?
Yes.
Yes, sir. You can see the curve.
Just follow. This is a hypothetical black body curve based on the Kirchhoff's model. So here in my x-axis, that is a lambda, that is micrometer. What I have told you, what is the range of our nanometer or visible band? 380 to 780. So here just it is in a very lower scale. We have made it 0.4 to 0.7 micrometer. Okay. So this line, so if you follow, so this is basically the region of our visible band. So visible band has been shown. And here the power densities are represented as a function of wavelength. Now, just see, once the black body is operated with 1000 K, so this is your curve. This is what we call spectral power density distribution. Spectral power, this is a spectral power. That means what a fraction of input energy is converted as output. So watt per meter square, so that is 1000 K. Okay. Now, so can anybody tell me this 1000 K, how much you can see as a light?
No.
Nothing, right?
No.
Now, once I am increasing the temperature from 1000 to 2000 K, it will be shifting towards the shorter wavelength. So now can you see some amount is coming under 0.4 to 0.7 region? So that is light, right?
Yes.
Now if we operate that with 3000 K, this will be, and at 5000 K, what is happening? What is the beauty if the same black body operated at?
In the visible range.
Yeah, the peak is now under light. So that means here we are going to get more and more light. But while we are talking about the efficiency or energy conservation, we will be considering the total, the light, ultraviolet, heat, everything we need to take care of. Okay. So that is why whether I'm going to get the light or not. And one more thing I have forgotten, next definitely I'll be going to tell you that once we are talking about the black body models, don't think that there will be some universal black body model present. The black body models are always applicable for a small region of frequency for which the black body is there. You will never be able to see a black body which is always for visible region, for ultraviolet region, for IR region. Every time it's for the entire wavelength, it's an universal black body. This is not possible. Okay, so mostly the black body, whatever we have, those black bodies are basically for a particular region for which we can declare. So the region is defined like frequency. All the models, the Rayleigh-Jeans model, Kirchhoff's model, Wein's model, Max Planck's model, every models, whatever we have for the black body till date, all the models are only applicable for a small range of frequency. So you can't use for all the range, or you cannot make it universal. Okay, so that's why here maybe a black body which at the lower temperature doesn't work like a light, just our example. But if we increase that, it will become more and more light. So the light component will increase. But while we are calculating the energy conservation point of view, while we are calculating the efficiency point of view, we need to take care of the entire components, the light, non-light, all. But while we are going to talk about the light, so that's why I told you that here we need to introduce a term called efficacy to know how much fraction of the input energy is getting converted as light. I am not interested about how much of input is getting converted as output. That is another parameter. There is definitely, I can't say we are not interested with this. We are, but for as a light source, we are more interested to know how much fraction is getting converted as light. Are you getting my point?
Sir, can you please explain what's the y-axis? What's the
Wow.
parameter?
Yeah. This is basically not intensity. We will call it spectral power distribution. So here you will see the watt, this n lambda. We will be talking a lot and we will be solving many numerical problems on this. So that's why be specific that spectral power distribution term is a input which is applicable for all type of radiators. Okay, so the unit is watt per centimeter square per micrometer. The micrometer is, I think you will be able to relate, this is a distribution. If you just find the area under the curve, the micrometer and micrometer will cancel out each other. So what will be the unit then? Watt per centimeter. So this is basically the spectral power distribution. Spectral power density or power density. What is the input power and centimeter? So that is my x-axis. Basically, we have wavelength, and y-axis we have spectral power distribution, abbreviated like SPD. Okay, power density. Sometimes even this is equally applicable for our light source. So that's why I want to make a call to all of you that while we are talking about that, we will be never talking about light or something. We will be categorizing the entire thing like a radiator. Okay, so for any light source, it is a radiator. Even if the source doesn't behave like a light, then also it's a radiator. So while we are defining a radiator, the most fundamental technical term we need to use is the spectral power distribution or SPD. Okay, so is it okay, clear? So that's why the watt per, don't think that it is always required for your source. Now, sometimes I need to make my camera on to tell you that we are connected, but if we make my camera on, the size will be more. So I will be sharing the video if you want, because I am recording that, the recorded one I will be sharing if you are interested with. So here, that is one important part. Once we are talking about this entire amount, maybe under visible region, may not be, but we need to represent them in this way. So just wait, if it is operate. That's why the spectral power distribution term is equally applicable for any other light source also, because light source is fundamentally a radiated tube. So out of that, how much light is there, that we will see how to calculate that. This is the topic relating lumen to watt. Today I don't want to continue because this will take lots of time. But before I conclude today, this particular curve I want to explain. Such a way we can jump to our this relating lumen to watt. The watt is an input electrical power, and I want to know how that can be related with the luminous flux output. So before we jump to this portion, let us talk about this portion very clearly. With this, we will conclude. So in this case, in my x-axis, already I have seen. Can you see the both the curves, the red and green?
Yes, sir.
Yes.
So here, this is nothing but the human eye curve. Though the CIE standard photometric observer, this was written. So what is CIE? CIE is Commission on Illumination Engineering. So they are the biggest body, worldwide body, who are referring different standards. They are doing lots of research. They are recommending something. So that's why just the way we have our national BIS, Bureau of Indian Standard, CIE is the forefather of them. That means CIE, basically is taking care of mostly European country, and for the rest of the country, especially for America, they have their own standard, IESNA, we call Illumination Engineering Society, IES, North America. They call Illumination Engineering Society of North America. So please be connected with that two terminology, because many times we will be using CIE and ISNA. So those are nothing but two regulatory body, two standard body who are developing different standards and recommends different requirements. So that's why the CIE and ISNA we need to refer many times. Now let us think about that. So in this case, the red curve, if we follow, that is nothing but in x-axis we have wavelength between 380 to 780 nanometer, and y-axis we have spectral luminous efficiency curve. So that is human eye response. So it is, the value varies from 0 to 1. For the red curve, that means what I have told you a few minutes back, that 380 to 780 nanometer, what our human eye can see. But 380 to 780 nanometer human eye definitely can see, but not in a very uniform way, because the distribution of rods and cones in our eyes are not uniform, and their sensitivities towards different wavelength, even the cones who are the pigmented one, sensitivity of that with the different wavelengths are not uniform. So that's why we have a very different characteristics curve of human eye. So that eye sensitivity, if we plot, this will be peaking at 555 nanometer, and the value will be minimum at 380 to 780 nanometer. The question definitely will come that once we are talking about the human eye characteristics, it definitely will differ with the individual, it definitely differ with the different age. So, but this is a sort of standard average curve. The deviations will definitely be there. But while we are calculating something, we'll be referring that we need to standardize something. So CIE with a very set of observer, they have practiced the experiment, and finally they have got this characteristics curve, the red one we call the photopeak curve. That means if you have sufficient light in your surrounding, so under this condition, whatever curve we will be having, that is a red curve. We call it V lambda, V in bracket lambda. So V is a, basically this is nothing but the human eye sensitivity curve. So which will be peaking at 555 nanometer. Mostly related with your cone cells, but very few contribution of rod cells are there also. On the other way, if you have a dark condition, your rod cells are somewhere becoming more active because your your light level has reduced significantly. So under this condition, the curve will be shifting from the red to the green one. This is what we call scotopeak curve. So the peak of this is also same human eye characteristics curve. So the moral of the story is that your human eye curve also shifts with the different color, different light level. So if you have a different type of light level, so this value will definitely vary from the red to the green, and the green curve is called V dash lambda or scotopeak, and the peak value, peak sensitivity towards that scotopeak one will come at 507 nanometer. So while we are going to refer the human eye characteristics, we should know what is the light level we have. Based upon that, we will be considering whether we are going to take V lambda curve for the photopeak response or V dash lambda curve for the scotopeak response. So that too we need to individually identify. So that is many times, again and again, I am telling you in coming days, we are going to refer that to human characteristics curves several times. Photopeak one we need to use everywhere. But there is, just for your information, there is another curve exists between the photopeak and scotopeak we call mesopeak one, that helps whether if you have a exactly like photopeak or whether you have neither scotopeak, it's in between the photopeak scotopeak region. That is what we call mesopeak one. That is not included in your curriculum, just for your knowing that during night time while we are driving our car in a street, our visions are, our light level is not that high, such a way we can declare it's a photopeak condition. It's not that poor, such a way we can declare it's scotopeak one. It's an in between the photopeak and scotopeak, that's what we call mesopeak one. So that's why in a nighttime driving situations, in a nighttime movement situations, whatever we have, mostly that is under mesopeak. But we need to now focus about the photopeak curve and the V lambda and the scotopeak curve. This is a human eye response curve. So that will be used like a filter for our coming light related calculation. Next day, once we will relate the lumen to watt, then also we will see. Once we are going to calculate the flux, light flux, that will be used. Once we are talking about the different light instruments like lux meter, very unfortunately, I can't show you the lux meter in our laboratory. If the situation was normal, if you could have come to our laboratory, possibly you will be able to see the light meters, but unfortunately, you couldn't see. Definitely, I hope in near future we will meet in our lab and we can see. So there we'll see the lux meter we call the fundamental raw elements what we have. Apart from that, there is a raw photoelectric sensor. We need that filter also. So this is we call V lambda filter and V dash lambda filter. We'll be coming to those topics in the coming days more elaborately. So I hope today we can conclude our session from there. Maybe little interruptions, the technical interruptions from internet we had. But with this today we can conclude. I will be sharing that PowerPoint presentation to you. But again, I am telling you that unfortunately I don't have any note. You have to go through the textbooks. This portion, especially for the radiation portion, I'll be referring the Joseph Murdoch's book. So that the author is Joseph Murdoch. So the book is there with me. Once maybe Anish or maybe Rohit, whoever will come to me, I'll be sharing that to you. So such a way you can circulate the photocopy, maybe in a soft copy mode also among your friends.
Okay, sir.
Presently, I'm sharing that PowerPoint presentation, whatever the other presentations I have with all of you, such a way you can refer for your coming days. So that's all for today. So if you have any query, just feel free to ask. I know that you are missing your lunch time, possibly you are feeling hungry. So, but I'm helpless too because I couldn't take few of the classes because of my health issue. So if you have any query, just feel free to ask.
Sir,
yeah,
we can have the practical experience by video call. I mean,
okay.
Those instruments we can see them.
Okay, definitely. I have already prepared a PowerPoint slide such a way directly you will be able to see, and video call definitely will be there. But I hope maybe after the situation will be normalized, at least I'll take all of you to the lab, because that is you all should be very much proud about. This is our asset of our department. So we, from our department, you are also a component of our department, as we are. So definitely you will be very much proud to know that our department have this photometric laboratory. In India, no academic institute have. The big dark room. So if I can take all of you, maybe in a phase-wise manner, whatever protocol will suggest, and show you the instrument, how they works. Maybe whenever it is possible, I will try to take. Otherwise, the video call-based system, I will definitely adopt.
Okay.
Anything else?
No, sir.
So, any doubt, any query, any kind of input? The technical glitches, whatever we had today, unfortunately we were, but I hope you have got some kind of idea about the topic.
Yes, sir. We have got.
Okay, if you don't have any query, then we can conclude.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.